Hi everyone, today we are going to look at this Ampere's law. So Ampere's law is another way for us to calculate the magnetic field, okay, magnetic field. But in order to apply this Ampere's law, there is a very important criteria that we have to meet, that is the symmetry. Okay, the symmetric condition must exist. Okay, symmetric conditions, it means that the magnetic field is the same along the Ampere path. Okay, same along the Ampere path. Okay, later I will explain to you what is the meaning of Ampere path. So this is a path just like the Gaussian surface that you have to draw, okay, before you determine the magnetic field. So this law is very suitable to be applied for infinite line. Okay, so if this is an infinite line, you have a positive, it is extend to positive infinity and extend to negative infinity. So by using your right hand, you can determine the directions of the magnetic field will be in this way if your current is going up. Okay, so when I say symmetry, it means that all the point, okay, along this Ampere path, it will have the same value of magnetic field. Okay, so this Ampere's law is suitable for infinite line and also infinite surface. Okay, so this is something that we didn't learn in the Biot-Savart's law. Okay, so later on you will see, okay, when there is a current flowing on this surface, and this is an infinite surface, okay, you can use this Ampere's law in order to calculate what is the magnetic field, okay, at the top and also at the bottom of this surface, right? Okay, so what does this Ampere's law says? So Ampere's law says that the line integral, okay, line integral look like this. Okay, so this is the line integral, the L, okay, the line integral, okay, of the tangential component of H. Okay, tangential component of H, it means, okay, now let's say, okay, I have a current filaments. Okay, so this is my wire or current filaments. Okay, so my current is flow in these directions. Okay, so by using my right hand, okay, I know that this will be the direction of my magnetic field. So tangential component, it means that if you put this thing, okay, in a 3D coordinate system, this is y and this is x. Okay, so these directions, okay, will be the phi directions if we are representing using the cylindrical coordinate systems. So this one is the tangential component. So it means that the h in the phi directions, okay, tangential component, okay. So the tangential component of h around a closed path, so around a closed path, okay, so this is the h, okay, is the same as the net current that is enclosed by the path. Okay, it's same as the current that is enclosed by the path. Okay, so this is basically the Ampere's law. Okay, so this one, Ampere's law, is used, okay, when we want to determine the magnetic field, and we have to make sure that the current distribution is symmetric. This is what I mean just now. Okay, so here it means that if we integrate, okay, this magnetic field in the closed loop, okay, in the closed loop, we'll be able to get the I, okay, the I that is enclosed by the loop, okay, the current that is enclosed by the loop. Okay, so this is the general formula for the Ampere's law. So if you write the Ampere's law, okay, by applying the Stokes theorems, okay, so Stokes theorem says that we can transform the line integral into surface integral. So the h over here will become the curl of h. And if you relate, okay, the current enclosed by the Ampere path, okay, and also the current density, okay, the current density. So this is the current density from the surface, okay. We could say that this one, okay, the curl of the vector h is equals to this J current density. Okay, so this is also Ampere's law, but we write it in the differential form. Okay, we write it in the differential form. Okay, so to determine the magnetic field at one positions, okay, we have to first thing, okay, construct a Amperian path. Okay, so this is the case. Okay, so now you have current filaments over here. Okay, and you can see that the current show is going up. Okay, by using the right hand rules, we can estimate that, okay, the magnetic field will be a circular loop, okay, just to round this current. Okay, so let's say now if I want to find the magnetic field at this position P, I have to draw the Amperian path. So this is representing the Amperian path. Okay, so this Amperian path will touch the positions, okay, of my observation point. So all the magnetic field that is along, okay, this Amperian path, they will have the same value. Okay, they will have the same value. Okay, so this Amperian path is quite similar to the Gaussian surface that we draw, okay, in chapter 1 electrostatic, before we want to find the electric field at one positions. Okay, but in Ampere's law, it is not Gaussian surface. We call it as an Amperian path. Okay, Amperian path. Okay, so now let's use this Ampere's law to define the magnetic field equations for these infinite line currents. Okay, so let me draw a 3D diagram. Okay, a 3D diagram here. Okay, so now imagine you have current filaments over here, and you want to find out what is the magnetic field, okay, at this position P. Okay, at this position P. Okay, so we will apply the Ampere's law. So Ampere's law says that if we integrate the magnetic field, okay, so if the current is going up, the magnetic field surround the wire or surround the elements will be in these directions. Okay, so you can see that this is the magnetic field. Okay, so if we integrate the magnetic field in a closed loop, so over here we need to write down what is the magnitude of the magnetic field and its directions. Okay, so this one represents the direction. So this is the phi directions if we use the cylindrical coordinate to represent these directions. And for the dl, okay, is the length, okay, the length of the Amperian path. Okay, so the length of Amperian path. Amperian path. Okay, so obviously this Amperian path, okay, is in the circular shape. Okay, it's in the circular shape. Okay, so here we need to define or fix a coordinate system which can describe, okay, the length of this Amperian path. So in this case, I choose to use a cylindrical coordinate system. Okay, so if you look at the cylindrical coordinate systems over here, okay, cylindrical is here. So we look at the DL. So the DL is here. Okay, so your length, okay, your length is in what directions? Your length is in the phi directions. Okay, the Amperian path, okay, is in the phi directions. So the DL, I'm going to replace it with R d phi. Okay, R d phi. Yeah. So over here, this one will become R d phi here. Okay, and this one showing the directions of your path. Okay, so when we dot product, okay, two vector in the same directions, okay, we will get 1. Okay, we will get 1. So if you take out the h and r and integrate from 0 to 2 pi, because this is a complete circle, okay, it's a complete circle. So the angle for a complete circle is 2 pi, so we will get this one. Okay, so it means that our I is equals to h, okay, which is in the phi directions, multiply with 2 pi r. Okay, so our h will be equals to I over 2 pi r. And phi is here, the directions, showing the directions. Okay, so this equation is the same as the equation that we get by using Biot-Savart's law. Okay, and for infinite line. Okay, you can say that their equation is the same thing. Now let us look at how to derive the magnetic field for infinite sheet of current. Okay, so when I say that it is an infinite sheet, okay, it means that it is a planar. Okay, it is a surface and the size is very big. Okay, size is very big. Okay, infinity. Okay, so now this is a surface. Okay, you can see this surface, right? So you have the surface. Okay, very big surface. And imagine now on the surface you have a current flow. Okay, so the current flow on this surface, they are not given as I, but they are given as K. Okay, what is K? K is the current density. Okay, current density, and the K is in y direction. Okay, this is y directions. Okay, so you can see that all the current, okay, current is flow in the y directions. Okay, so if we don't draw these infinite planar, okay, in a 2D view, okay, this is what you will see. Okay, this is a 2D view. Meaning that you see this planar from here. Okay, you put yourself here. Okay, so you can see that the current is coming to you. Okay, it's coming to you. Okay, that's why over here we are using this symbol. Okay, the current is coming out. Current coming out. Okay, it's pointing to you. And there are so many current filaments. Okay, 1, 2, 3, 4, 5, 6, 7, and many more. Okay, all these, they are representing the current filaments. Okay, current density. Okay, so for each of the current density, if I zoom in, you can see that there is a red circle. Okay, and this red circle actually represents the magnetic field. Okay, surround each of the current density. Okay, so the direction, you can see the arrow, right? So the direction of the magnetic field, okay, is determined by using your right hand rules. So this one showing the directions of your magnetic of your current, okay, of your K, sorry, of your K. Okay, and the K is coming out, so you can take out your right hand and your thumb is pointing to yourself. Okay, your thumb is pointing to yourself. Thumbs point to yourself. Okay, so the other 4 fingers, you will find that they are rotated in the counterclockwise direction, just like this. Okay, counterclockwise direction. And this is the same thing applies for the others current filaments. You see all the current filaments, all the current K, current density. Okay, they are same thing. Okay, and if you check carefully, you can see this thing. Okay, so the magnetic field, they are in the opposite directions. Okay, opposite directions. Okay, and that cancel each other. Cancel each other. Cancel each other. Okay, cancel each other. So as a result, you will only see magnetic field at the top. Okay, at the top, you see, they are all going to the left hand side. Okay, or going to the positive X directions. And for the bottoms, okay, they are all moving and pointing to the negative X directions. Okay, and there is no magnetic field at the side. Okay, because it has been cancelled out and the planar, the surface is so big. Okay, so there is no magnetic field at the side. Okay, no magnetic field. Okay, this one, no magnetic field. No magnetic field at the side. So let's use the Ampere's law to define the equations for this infinite planar. Okay, that has the current density K flowing on it. Okay, so what Ampere's law says? Ampere's law says this. Okay, if we integrate the H in a closed loop, we are going to get the I that is enclosed by the loop. Okay, so in this case, we don't have the I, but we have the K. Okay, so K is the current density. And the current density unit is ampere per meter. So this is telling us how many currents in 1 meter. Okay, so if you look at this one, okay, if you look at this one, okay, so it is telling us that how many current in 1 meter. Okay, how many current in 1 meter. So if we want to relate it with the size, okay, with the size of the planar, okay, let's say that, okay, now I form an Amperian path, okay, over here because I want to find the magnetic field here. Okay, so I form the Amperian path, okay, which is in the orange color. So if I want to know the total current, okay, that is coming out from this Amperian path, I will multiply K with B. Okay, because the B is representing the length, okay, the length of this Amperian path. Okay, so I will multiply it with KB. And then I will start to integrate the magnetic field. Okay, so there are 4 points here. 1, 2, maybe I will erase it so you can see better. Okay, so there are 4 points here. 1, 2, 3, and 4. So I'm going to integrate from point A to point B. Okay, point A to point B, there is 1, 2, or yeah, from 1 to 2, or it's not AB, from 1 to 2, and then 2 to 3, 3 to 4, and 4 to 1. Okay, so for 1 to 2, okay, remember the magnetic field cancel each other. Okay, so there is no magnetic field from 1 to 2 and 3 to 4. Okay, 3 to 4. No magnetic field. Okay, they are 0. So you see there is a 0 here. And for 2 to 3, okay, from 2 to 3, okay, the magnetic field, okay, if you use your right hand right, okay, the magnetic field will be these directions. Okay, so the magnetic field is in the negative x directions. Okay, negative x directions. Okay, negative x directions. So if I write it here, okay, my H in the negative x directions, and I dot product with the dx. Okay, so the dx, okay, you are actually integrating because the length is b, right? The length is b. So just imagine you are integrating from b to 0. Yeah, for example, b to 0. Okay, so the direction is also negative x directions. So b to 0. Oh no, the direction, okay. Yeah, this direction should be positive. Okay, so you will have this H and then 0 minus B. Right, 0 minus B. So you have a negative. Okay, so you have negative H and negative B here. So you will have HB for this path. Okay, path 2 to 3. Okay, 2 to 3. So you have HB. And for path 4 to 1, okay, over here, so you integrate the magnetic field. So the magnetic field is in the x directions. Okay, and the length is also dx. So you are integrating from 0 to B. Okay, 0 to B. Okay, so this is directions. Okay, so you will have HB. Okay, so HB, that's why over here you have HB. Okay, when you add them up, you will have 2HB. Okay, so when you put this 2HB with this KB together, 2HB equals to KYB. So you can cancel this B. and your h is equals to ky over 2. Okay, so this is representing the magnitude. Okay, so the magnitude of the magnetic field. Okay, if you want to know its directions, okay, this is the directions over here. It depends on whether you want to find the magnetic field at the top, okay, this is at the top, or you want to find it at the bottom. Okay, so the general equation to find the magnetic field will be this one. Okay, so 1 over 2k, okay, is the magnitude, and you have to cross product with the directions. Okay, with the directions, okay, that is pointing from your plane surface to the point that you want to find the observation, you want to find the magnetic field. Okay, for example, this is your surface, and now you want to find the magnetic field at this position. So you will draw an arrow pointing from your surface to these positions. So if I'm using this coordinate system, this is x, for example, and this is z. So this n is equals to z directions. But if you want to find the magnetic field here, for example, so the arrow now will be pointing downward, so the n will be equals to negative z directions. Okay, and this is the things that you have to substitute here in order to find the magnitude, okay, and the value of the magnetic field, okay, that is from your infinite surface. Alright, so now let's look at exercise 1. So you have a plane z equals to 0. So z equals to 0 represent the locations, okay, the location of the plane. And this plane carry current density, okay, in the negative x direction. So you have to find the magnetic field at this position and also this position respectively. So first of all, let us draw out this plane. Okay, so I'm going to draw the plane. Okay, so this is the plane. Okay, so this is a plane and it is located at the position z equals to 0. Okay, so this is y, this is z, and this is x. Okay, so z equals to 0 is here. Okay, plane z equals to 0. And now you have your current density in the negative x directions. Okay, so negative x is in the opposite directions, meaning that the current is flow in these directions. Okay, and it is negative 10x. Alright, so now you have to find the magnetic field at two positions. Okay, the first position is 1, 1, 1, and the second position is 0, negative 3, negative 3, and negative 10. Okay, so these are the two positions that you need to find the magnetic field. Okay, so here you have to remember that the size of your plane, okay, the size of the plane z equals to 0 is infinity, infinity, meaning that it is very, very, very big. Okay, so in order to determine the magnetic field, okay, we have to apply this formula. 1 over 2k, the vector cross product with the n. Okay, so to make us easier, okay, especially when we want to analyze these components, I will draw this diagram into 2D. Okay, so this is 3D. Okay, so now I'm going to draw 2D. Okay, so you have to look at this plane from here, okay, from these directions. Okay, you cannot look from here. Okay, if you look from here, you cannot see the directions of the current flowing, okay, because the current is horizontal in this way. So you cannot view from here. It is either you view from the positive x directions or you view from here. Okay, the same thing. Okay, later I will show you. Okay, they are the same thing. Okay, so first of all, Let us view from this side. Okay, from position 1. So when you view from position 1, basically you see axis Z, right? And also axis Y. Okay, so these are the things that you can see. Okay, so now let's draw the axis. Okay, so I'm going to draw the axis Z. Okay, and then I will draw the axis Y. Okay, so these are the axes that you will see. And beside the axis, you can see the plane, right? Okay, maybe you will see this part, right? You can see this side. So you have to draw this side. Okay, so let us draw this side. So I'm going to use different colors. Might be red color. Okay, all right. Okay, so you see this plane. Okay, you see this plane. So this is your plane, red color. Okay, over here. Okay, so you see this edge, right? Okay, so I'm drawing this plane. Okay, I'm drawing this plane. So this is your plane. Okay, and you can see the position of your plane is located at the position Z equals to 0. Okay, very clear, right? So next thing, we are going to draw our current density. Okay, where is our current density? Okay, so this is our current density. Okay, this and also this. And we are going to draw them in our 2D diagram. Okay, so because we view from side number 1, so what we will see is, okay, so current density is going into the negative x direction. Okay, so the current density is going into the negative x directions. Okay, so we are going to use this symbol to represent that the current density is going in. Okay, it's going in. So we are going to go to that. Wait, okay, right. So we're going to draw this current density using this symbol. Okay, so this shows that, okay, the current is going in. Okay, going in. Right, current going in. Okay, so now you have to define, okay, or find out the magnetic field at position 111. Okay, since you are drawing, okay, a 2D diagram that has only z-axis and y-axis, so for the 111, okay, you only need to look at its positions of y and also the z. So one might be here, one might be here. So this is the positions, okay, of 111 that you need to find out its magnetic field. Okay, so by applying this formula, okay, 1 over 2 k and cross with the n. Okay, so we are going to take the k that is given by the question, negative 10x, right, and cross product with the n. Okay, so now I want you to pay attention on how to define the positions of n. Okay, so you must point, okay, from your surface to the observation point. Okay, draw an arrow. Okay, draw an arrow and you can see that from your plane to the observation point P, your arrow is in the positive z direction. So you make this thing to become positive. Okay, so this is how you determine, okay, the direction of unit vector n. And for this one, okay, it will be equals to 5. All right, equals to 5. And for the position, so x, z, you are going to get negative y. Negative and negative, you are going to get positive y. So this is the magnetic field, okay, that you can observe at the positions P, okay, 1, 1, 1. Okay, this is the first positions. Okay, so go back to the second position. So second position is 0, negative 3, and negative 10. Okay, 0, negative 3, and negative 10. Okay, so we are referring to position y and also the z. Okay, so for these positions, okay, negative 3 might be here, negative 10 might be, okay, I will just slightly extend it, might be here. Okay, so this is the positions 2. Position 2, this is position 1. Okay, so we are going to use the same formula. Okay, very easy formula. Okay, cross with the n. Okay, so this part is exactly the same, negative 10x. Okay, so the different thing will be the n. Okay, so in this case, how to determine your n directions? So you have to point again from your surface to the observation point. Okay, so this is your observation point, and you can see your arrow is going down. Okay, going down, it means that it is in the negative z directions. Okay, so you need to put this thing as negative z. Okay, negative z, and then okay, this one will be 5. Okay, so this one, because we got a negative, so this one will be negative y. Okay, so negative y. Okay, so this one will be your magnetic field at the second position, 0, -3, and -10. Okay, so you can actually determine the directions also, okay, by using your right hand. Okay, so this one showing the direction of your thumb, so you put your thumb into, okay, well, you put your thumb into the surface, and you can see your other forefinger is showing in these directions. Okay, so showing in this direction, which is the positive y directions. Okay, so and for the on the other hand, and for this one, you can see that, okay, when you point your thumb into the page, okay, the other forefinger will go to this side. Okay, we'll go to this side, which is the negative y directions. Okay, so this is how you determine the direction of the magnetic field by using the right hand. Right, so this is not that difficult, right, to find the magnetic field, okay, from a surface that has a current density. Alright, so now let's look at how to use the Ampere's law to find the magnetic field within an infinite long coaxial transmission line. Okay, so coaxial transmission line is actually a wire. I can say that it is a wire, but we only use this wire at high frequency. Okay, so we are using this coaxial line to transmit signal at high frequency. So this is the structures of this coaxial transmission line. Usually you will see this thing a black rubber actually covering the inner structures of this coaxial line, and if you open it up, you can see that there is a braided shield. Okay, so this one is for the shielding purpose, as well as this one, okay, in order to protect the wire inside. And after the foil shield, you will see that it's a dielectric. So usually the dielectric within the coaxial transmission line is Teflon, and the Teflon is used to support, okay, the inner conductor. So in this case, your coaxial transmission line will have an inner conductor, which is this part, and also the outer conductor. Okay, the outer conductor, okay, is this part. Okay, the foil shield and also the braided shield. So if you view it from this side, okay, you see this thing from this side, you can see that there is an inner conductor over here, and there is an outer conductor here. Okay, so this outer conductor consists of the foil shield, the braided shield. Okay, so you will have an inner conductor, and also this is the outer conductor, and over here in between the inner and outer, you have dielectric. Okay, you have dielectric material. Okay, so we are going to see how to use this Ampere's law in order to determine, okay, the magnetic field at different region. Okay, at different region, you can see this thing. Okay, so this is what I say. Okay, the outer conductor, and this one is the inner. Right, this is the outer. Okay, so we are going to see the magnetic field at a few portions. Okay, first one is when the R, okay, is less than the A. Okay, so this is the first portions that we can see what is the magnetic field. And then, okay, we are going to see the area, okay, in between A and B. Okay, so what is the magnetic field in these regions? Okay, and also we are going to see what is the magnetic field in this region. Okay, these regions, okay, that is in between the B and also the B plus D, and also outside of it, okay, by using the Ampere's law. Okay, so this is a description about the things, and this is the region that we are going to see what is the formula that we can use to find the magnetic field. Okay, so this equation is actually coming from the Ampere's law, which says that if we integrate the magnetic field in a closed loop, we are able to get the current enclosed by the Amperian path. Okay, so as a result, okay, I don't want to go into the derivations, but if you're interested on the derivation in detail, later I will share with you another video. Okay, but from this derivation, okay, we can say that the magnetic field in this region, okay, you can see that this is your Amperian path, okay, in this region is going to be I, okay, I is the current, okay, is the current, okay, P is the distance or radius you want to find the magnetic field, okay, and A is the radius of inner conductor. Okay, so just replace the value, you can get the answer. So this is for the case when this thing, okay, I will say this is a rho, okay, rho less than A, rho less than A. When we move on to the region in between A and B, which is this one, okay, so this is the Amperian path. So again, we use the Ampere's law. Okay, so the magnetic field is defined by this formula. Okay, I is the current, R is the radius that you want to know is magnetic field. Okay, right, so next we move on to the region that is in between B and also B plus T. Okay, B and B plus T, which is these regions. Okay, so the formula is a little bit complicated. Okay, so you have the I current, you have the distance, the radius that you want to know the magnetic field, right? And also the B is the outer radius, and T is the thickness. Okay, what is the thickness here? Okay, this is the thickness. Okay, you can see this is a T. Okay, T is the thickness of outer conductor, okay, of this coaxial transmission line, MBT, you know. Okay, so just replace the value, you could get the magnetic field. And last one is the region whereby the rho is greater than B plus T, means that it is outside. Okay, for this part, okay, the H or the magnetic field is equal to 0, meaning that there is no magnetic field outside of this long coaxial transmission line. Okay, so this is very important. Okay, when there is no magnetic field outside of it, it means that there is no radiation coming from this coaxial transmission line, which could affect the operation of the other instrument or the other devices. Alright, so there is no magnetic field. Right. Alright, now I'm going to introduce you a new term, that is the magnetic flux density. Okay, if you remember, we talked about electric flux density before in chapter number 1. Okay, so this magnetic flux density concept is similar as the electric flux density. So we all know that magnetic field can be generated when you have current. So if this is your current and your current is coming out from the surface, okay, so there will be magnetic field. Okay, so magnetic field surround the current filament. So this is the magnetic field, right? So you can determine the directions of the magnetic field by using your right hand rules. So you know that your other 4 fingers is actually pointing the counterclockwise directions. So we always represent our magnetic field by using magnetic flux line. Okay, so all this blue color one, actually we said that it is a magnetic flux line, which we use it to show that there is a magnetic field surround a current filament. Okay, so if you want to know the total flux that is passing through or go through a surface, okay, let's say now I have a surface here. So the the magnetic field is going into this surface, pass through this surface. If I want to know that the magnetic flux that pass through this surface, I have to perform these operations. That is, I have to integrate my magnetic flux density. Okay, the P is the magnetic flux density. Okay, with respect to its surface, it means that I have to multiply with the area in order to get the total flux, okay, that pass through this surface. Okay, so for this magnetic flux density, okay, this is the magnetic flux density, the unit is Webers or WB, okay, and unit of the unit of B is Weber per meter square. I'm sorry, but this one is the unit for the magnetic flux, okay, and for the B is Weber per meter square, Weber per square meter, okay. So there is a relationship between the magnetic flux density and also the magnetic field, which is this one. Okay, you can put two of them together by relate it with the property of the space, okay, that this magnetic field propagate. Okay, when it is mu naught, okay, this is mu, okay, I can pronounce this as mu, okay, mu naught, okay. So when it is mu naught, it is representing the permeability of the free space. So just like we did for this one, okay, if you want to know the permittivity of a material, okay, or a medium, we have to multiply the relative permittivity with the permittivity of free space. So this is the same thing over here. If I want to know the permeability of a medium, I have to multiply the relative permittivity of the medium with the permeability of a free space. So don't get confused on the word. This one is permeability and this one is permittivity. Okay, they are different. Okay, so in this chapter, magnetostatic, we are going to use the permeability, okay, to relate the magnetic flux density and also the magnetic field. If you really observe what happened to a magnet bar, right? Okay, so this is the gray color. Okay, so this is your magnet bar, right? So your magnet bar will have a north pole, you will have a south pole. Okay, so the magnetic field is always originate, okay, from the north pole and terminate back to the south pole, right? So we can say that this magnetic flux line always close upon themselves. It means that it start from themselves, okay, start from themselves and also end by themselves. Okay, and it is not possible to have an isolated magnetic dipole. It means that no matter how small I cut this magnet bar, okay, even I cut it into two, okay, I cut it into two, okay, so automatically this one will become north pole, here will be south pole, here also north and south. No matter how fine I cut the magnet bar, it is impossible, okay, to only have a north pole like this or south pole like this. I cannot split them. Okay, they will always combine each other. Means that no matter how small it is, you will have a north and south. So this is the meaning. Okay, it is not possible to have an isolated north pole and also south pole. So it means that the total flux through a closed surface is equals to 0. Okay, since this magnetic field is always terminate upon themselves. Okay, so if we put a very big surface, okay, out of it, we will say that the magnetic flux, okay, the magnetic flux density that pass through this big surface is always equal to 0 because it always terminate back to themselves. Okay, it never go outside. Okay, it never go outside. So this is the meaning. Okay, so the total flux that pass through a closed surface will be equals to 0. Okay, so this is one of the Maxwell equations, okay, for magnetostatic, coming from the magnetostatic. Yeah. So if you apply the divergence theorem, okay, divergence theorem is a transformation from the surface integral to volume integral, okay, because when after we transform it, okay, we know that it is equals to 0. So we can say that the divergence of the magnetic flux density is equals to 0. So this one actually also representing the same thing over here. Okay, just we write it in different form. This is the integral form, and this one is the differential form. Okay, they are same thing. Okay, so when we have this equation, we can say that the magnetic field line are always continuous. Okay, start from themselves and end at themselves. Okay, so these are the four Maxwell equations that we have learned for the static, electric, and magnetostatic field. Okay, so do you still remember this one? Okay, so this one is the Gauss law, right? The Gauss law. And what happened to this one, if you remember, when we do the derivations for the equations of capacitors, right? We did this thing, right? Okay, so if we integrate it in the closed loop, okay, the potential difference, okay, is equals to 0. Okay, so this is the conservativeness of electrostatic. And this one is the Ampere's law, whereby the total, if we integrate the magnetic field in the closed loop, we will be able to get the total current that is enclosed by the loop, right? And the last one is this one. Okay, this equation is telling us that there is no monopole magnetic. Okay, there is no existence of magnetic monopole. It means that there is no a single north pole or a single south pole. Okay, that is not possible for this to happen. So these are the four Maxwell equations for static, electric, and magnetic field. Right.